Welcome to this lecture on the trace of a matrix. Imagine you are looking at a massive, complex spreadsheet of numbers. What if I told you that you could understand a huge amount about how that entire grid behaves just by looking at one single diagonal line of numbers? In linear algebra, this simple but powerful shortcut is called the trace. Today, we are going to build your understanding of this concept from the ground up. We will learn exactly what the trace is, how to calculate it, and why it is such a magical tool for mathematicians, physicists, and computer scientists. By the end of this video, you will see that sometimes the most profound insights come from the simplest additions. Let us dive in. To begin our journey, we first need to understand the environment we are working in. We are dealing with square matrices. You can think of a square matrix as a perfectly balanced grid of numbers, where the number of rows is exactly equal to the number of columns, like a 2 by 2 or a 3 by 3 table. Now imagine drawing a straight line starting from the very top left corner of this grid, all the way down to the bottom right corner. This special path is called the main diagonal. The trace of the matrix is simply what you get when you add up all the numbers sitting directly on that main diagonal highway. Why does this matter? Because this one quick calculation gives us a single number that acts like a fingerprint for the entire matrix, unlocking deep secrets about its behavior without forcing us to look at every single entry. Now that we understand the concept visually, let us look at how we write this mathematically. The formula for the trace might look a bit intimidating at first, but it is actually just a set of simple instructions. On the left, TR of A simply stands for the trace of our square matrix A. On the right side, we see the Greek letter sigma. In mathematics, sigma is a command that tells us to add a sequence of things together. What are we adding? We are adding the terms A sub II. The letter A represents a specific number inside the matrix, and the subscripts tell us its exact address. Because both the row and column are represented by the same letter I, this guarantees we are only looking at positions where the row number matches the column number, which is exactly our main diagonal. The n at the top just tells us the total size of the matrix, so we know when to stop adding. Let us make this formula completely concrete by looking at a visual representation. Here, you are seeing a standard 3 by 3 matrix. Notice how the elements are labeled with their row and column numbers. The top left element is in row 1, column 1. The middle element is in row 2, column 2. And the bottom right element is in row 3, column 3. That thick orange band highlights our main highway, the main diagonal. As you can see, every single element inside that orange band has matching row and column numbers. The diagram perfectly illustrates our formula in action. To find the trace, we completely ignore all the numbers outside the orange band. We just take the numbers inside it, add them together, and we have our result. It really is that straightforward. Before we move on to more advanced properties, let us see this with a concrete example. We are given a specific 3 by 3 matrix, which we will call matrix A. Our goal is to calculate its trace. The first row has the numbers 4, 1, and 2. The second row has 0, -3, and 5. The third row has 7, 8, and 9. Our strategy here is to completely ignore all the numbers that are not on the main diagonal. We only care about the elements where the row number matches the column number. So we look at the top left corner, which gives us the number 4. Then we look dead in the center, which gives us -3. Finally, we look at the bottom right corner, which gives us 9. These are the only 3 numbers we need. Now that we have identified our key numbers, let us finish the calculation. We write out our trace formula for a 3 by 3 matrix, which tells us to add the elements from the first, second, and third diagonal positions. We substitute our exact values into the equation, 4 plus -3 plus 9. Performing the basic addition, 4 minus 3 is 1 and 1 plus 9 equals 10. So the trace of this entire matrix is simply 10. This single number, 10 is the fingerprint of our matrix. As we will see later, this simple result actually tells us what the complex stretching factors of this matrix would add up to, even though we have not done any complicated math to find them. Now that we have successfully calculated a trace, we need to look at its special rules, known as properties. These properties are what make the trace an incredibly powerful tool in algebra. Why? Because the trace behaves very predictably when we mix different matrices together. Instead of having to do massive, complicated matrix calculations first and then finding the trace, these rules often let us take shortcuts. The two most important rules we will cover are the linear property and the cyclic property. The linear property deals with what happens when we add matrices together, while the cyclic property reveals a beautiful secret about what happens when we multiply them. Let us explore exactly how these two rules work. To see these rules in action, let us first look at the linear property. Here, A and B represent two square matrices of the exact same size. The left side of the equation tells us to first add the two massive grids together to create a brand new matrix and then calculate the trace of that result. The right side offers a different path. Calculate the trace of matrix A all by itself, calculate the trace of matrix B all by itself, and then just add those two regular numbers together. The equal sign guarantees that both methods will always give you the exact same final result. Think of it like weighing two bags of apples. You can put both bags on the scale at once, or you can weigh each bag separately and add the weights together. The total weight is identical either way. Now, let us look at the cyclic property, which is even more fascinating. In this formula, AB means we are multiplying matrix A by matrix B. Matrix multiplication is usually very strict about order. Multiplying A times B almost always gives a completely different grid of numbers than multiplying B times A. However, this formula reveals a beautiful secret. Even though the full grids of AB and BA are completely different, the sum of their main diagonals will always be exactly the same. This is called the cyclic property because you can take the last matrix in the multiplication and cycle it around to the front without changing the trace. This even works for three matrices, A, B, and C. You can shift them in a circle, moving C to the front, and the trace remains unchanged. Before we move on, let us prove that this cyclic property actually works with a concrete example. We have two small 2 by 2 matrices. Matrix A has a top row of 1 and 2 and a bottom row of 3 and 4. Matrix B has a top row of 0 and 1 and a bottom row of 2 and 0. We want to calculate both A times B and B times A and then prove their traces are identical. First, we perform standard matrix multiplication to find AB. We multiply the rows of A by the columns of B. For the top left entry, we do 1 times 0 plus 2 times 2, which gives 4. We repeat this process for all 4 spots and we get a new matrix with a top row of 4 and 1 and a bottom row of 8 and 3. Continuing with our proof, we now look at the main diagonal of our new matrix AB. The top left number is 4 and the bottom right number is 3. Adding them together gives us a trace of 7. This is the first half of our proof. Next, we reverse the order and multiply matrix B times matrix A. We again multiply the rows of our first matrix, which is now B, by the columns of our second matrix, A. Notice that the resulting matrix is completely different from AB. The numbers inside are 3 and 4 on the top row and 2 and 4 on the bottom row. As expected, matrix multiplication is definitely not commutative. The grids are entirely different. Now for the final step of our verification. We find the trace of this new matrix, BA, by adding its main diagonal. The top left number is 3 and the bottom right number is 4. Adding them together gives us 7. Look at that result. Even though the two matrices look completely different from each other, their traces are exactly the same. Both equal 7. This perfectly proves the cyclic property in action. This is why mathematicians love the trace. It gives us a reliable, unchanging anchor even when the underlying matrices are shifting and changing order. So we have proven that the cyclic property holds. This brings us to one more massive connection we must make, and it involves something called eigenvalues. If you imagine a matrix as a machine that stretches and squishes rubber bands, an eigenvalue is a special number that represents exactly how hard that machine pulls. Finding these eigenvalues is usually a very long, difficult, and complex mathematical process. It is easy to make a mistake. But the trace gives us a magical shortcut, hidden in plain sight. It turns out that the simple addition we do down the main diagonal is deeply connected to these complex stretching factors. Let us look at the formula that links them together. Now that we know what eigenvalues are conceptually, let us see how the trace relates to them. In this equation, the Greek letter lambda is the universal symbol for an eigenvalue. The subscript I just means we are listing them out. The first eigenvalue, the second eigenvalue, and so on. This formula states a profound theorem. The trace of a matrix is exactly equal to the sum of all its eigenvalues. This means if you just add up the numbers on the main diagonal, you instantly know what all the complex stretching factors must add up to. If you spend an hour calculating your eigenvalues and they do not add up to the trace you found in 10 seconds, you immediately know you made a mistake. This formula we just saw leads us to an important question. Why does anyone care about this in the real world? The trace is incredibly important because it is an invariant. An invariant is a property of a system that does not change even if you look at the system from a completely different perspective or coordinate system. In quantum mechanics, which is the physics of atoms and particles, the trace is used to calculate the probability of different events happening. If you want to know the chances of an electron being in a certain state, you calculate the trace of a density matrix. It is also a favorite tool for engineers and computer scientists. Because checking the trace is computationally very cheap and fast, it is perfect for catching errors in massive computer simulations. We have covered a lot of ground today, so let us reinforce the most important ideas. First, the trace of a square matrix is simply the sum of the numbers on its main diagonal, running from top left to bottom right. It acts as a quick fingerprint for the matrix. Second, because of its linear and cyclic properties, it allows mathematicians and scientists to simplify incredibly complex equations by shifting matrices around without changing the final trace. Finally, it gives us the sum of a matrice's eigenvalues without having to do any complex math. You have now mastered the full concept of the trace. Whenever you see a square matrix in the future, remember that its most fundamental summary is just a simple addition problem down the middle. Great job!